up. In any case, I've listened to Eamon and later on to Bruno, and I kind of think that we lie very nicely into the optical stability arena in space and harsh environment. I'll just give a very short presentation as far as our background, and then I'll move directly to where we help and contribute in the atomic clock arena. We specialize in monolithic optics in harsh environment, whether it's space, whether it's military, shock vibration, but the most important thing is the stability. We are located in Long Island, New York. Unfortunately, these days, you hear about New York because of the wrong reasons, but we are trying to get through that mess, hopefully within a week to 2 weeks. So we are holding fingers, but this is a global crisis. So we'll go back to my presentation. PLX is the pioneer of a hollow retroreflector. I won't spend much time talking about the retroreflector, but we'll move forward with our company history. Goes back to 65 years ago, starting with a hollow retroreflector, and then in the last 10 years focusing in the space arena and the military arena with high stability optical structures. Integration to subsystems as well as full platforms. This is a really short presentation of the function of a retroreflector, but the emphasis is the function of sub-arc seconds accuracies in harsh environment. As Sana had mentioned earlier, this is an extension of retroreflector. It's a lateral transfer hollow retroreflector. Just to give a flavor of how this can be incorporated in the atomic clock arena by extending the optics and yet keep it very stable and allow any matter to go in between and have high stability. I'll show it next in the presentation of the monolithic optical structure technology. The applications that we cover is pretty much what you see here, going to our matter, where we are using M.O.S.T, which is a monolithic optical structure technology. This is a good example of a project we currently work with the US Observatory. Naturally, we have the several atomic clocks here in the US, but this is for 657 nanometer laser. The emphasis here is taking advantage of the highly stable optical assemblies in multiple folding of the laser. You can see on the left here, you have what I call the LTHR. On this side, you have a retroreflector. The matter goes right in between. In the right side, you would see additional folding. All of these foldings of the laser obviously requires high accuracies of alignment. The expertise we have is maintaining the alignment in different sizes and different materials, and with significant temperature impact and sub-arc second accuracies. This particular system as a whole is 1 microradian, so it's 0.2 arc second. This is actually an example of 2 retroreflectors that were positioned to be highly accurate. The laser would be actually right in between into an evacuated tube. This was made from ULE. The scalability is both with large optics and small optics. We're dealing right now with MEMS in different defense arena, and we are looking into the incorporation of MEMS into the aerospace as well, both with passive as well as static components. incorporating it into the monolithic optical structure would allow for that high stability. So we are focusing on maintaining the subarc-second accuracy while you still have thermal gradients. Femtosecond laser obviously would add additional challenges. So making sure that the optics will be hollow and will give us the proper reflectivity in different thermal intensities. That's our focus. As far as experience in integration, we do have some commercial experience associated with spectroscopy, FTIR spectrometers. This just shows how we incorporate these monolithic assemblies. This is like a structure. I don't know if you see the course of on the bottom left of the screen, you can see the monolithic optical structure technology in practice. That's a Michelson interferometer with a retroreflector incorporated. This is, I would say, 10 by 4 in terms of size of box, but the scalability to a smaller size is also available. We're talking about 2 millimeter in diameter of small retroreflectors, as well as the monolithic structures. This is just a flavor of some of the parts that we've made. When it comes to space, we do focus on lightweight optics, whether it's small or large. Some of the future applications which we've dealing with is in the LiDAR arena, both for aerospace and the autonomous vehicle. And this is a good example of incorporating MEMS into retroreflectors, so that would work for predominantly communication, friendly fire when it comes to defense. And again, just this is my last slide, just going back to what Eamon had mentioned before, as far as ESA projects with the atomic clock, what I would like to see, if it's possible, is participation in early stages of the technology development. I think that optical alignment is something that has been challenging for many reasons and for quite some time, and there is I think lack of appreciation at times of the stability that you can get from small as well as large optics. So we are focusing on subarc seconds in the environment that you are dealing with in space, and the heritage speaks for itself. So I think that if we would have the opportunity to support your projects, that might be a positive thing for PLX, but I think that you would be able to benefit from the stability and the longevity. Thank you.
Thank you very, very much, Itai, for this presentation. I already met you 1.5 years ago at Laser Munich, and I fell in love with the M.O.S.T technology, with the way that you integrate monolithically different optics, and having you in EPIC is a huge opportunity for the companies who are developing high-end optics, high-end mirrors, but also a good opportunity for the companies in the higher part of the value chain, companies like Biosystem and the Space Agency. We have you now as the link that hold these two worlds together. What can these people today in the room, what can they do for you, and what can you do for them?
I think I touched as far as what they can do for us. I think early participation in general, I think that it's not just true for ESA. I think that collaboration between companies, and thanks to EPIC and Jose's energy, I think that we've already felt the impact. I think that early participation with the understanding of the core technology and what each individual company can contribute would be almost a must for success in projects. As far as what we can do for them is essentially the high stability, high accuracy, and performance. I think with us, it's really all about performance.
Do we have any questions for Itai? Yes, Jax.
Yes, I would have a question. So you've shown a nice picture of the first prototypes of the atomic clocks made by NIST or the magnetometer, and you say that you could, with your monolithic optics, be of help for improving perhaps some kind of optical light transmission in such small devices. How could you do that?
I'm not sure I understand the question. Sorry.
You've shown in one of your slides, I think it was just prior to the case 4 study, and there was a picture of the device that NIST was developing. I think it's a magnetometer or an atomic clock, and somehow you could integrate your optics there inside. And my question is, what would that bring, and how would you do that?
How we do this is not something I necessarily can elaborate much, but as far as what we've done there is the combination of multiple optical elements in a sandwich structure. I didn't really present it here in the presentation, but if you actually go to our website, in the very first page, there is a very short video that shows ultimately how we do this in a very broad characteristics. It's a sandwich structure, top and bottom plate, where you combine all of the optical elements with very similar CT matched materials.
Okay.
That's as far as maybe as close as I can get as how we do it. But it's more about the incorporation of the optics into the next level assembly. So it's really important to understand that while you can achieve the sub-arc second accuracy, you can achieve it even with mirror mounts. You know that very well in lab. The next morning you come into the lab, that's already out of accuracy. So achieving it is good, but actually incorporating it in the next level assembly, whether it's in an aircraft, whether it's in a space application, that's really our expertise. So we do work together with company like yours and to understand the application first, and then we would advise how we structure it. But again, our website will show different models and options and projects that we've participated in the past.
Thanks so
Hopefully
much.
to answer your question. I'm not sure that.
If you ever had the chance of holding one of the retroreflectors of PLX, you will be amazed. First of the stability, but also the beauty. They are beautiful. We have a question from a newcomer to Epic, Serge, Orolia, Switzerland. Thank you for coming to this fantastic family.
Thank you for the invitation. I have a question because we are working at Orolia on the space clock for, it's called an ion trap, Mercury ion trap. And we work in the UV at 200 nanometer. Mm-hmm. And we need optics for the space application. And do you provide lengths or at this wavelength?
We do provide optics in this particular wavelength. We don't manufacture lens spheres. We do get it from other suppliers. We do the manufacturing in-house for our assemblies. We do the coating, but when it comes to lenses, that's not something that is our expertise.
Oh yeah, but a reflector, yeah.
Absolutely. We've been working in that in that range, and we do the coating for that range. And again, the scalability is inherited in the technology.
Okay, thank you.